It's an undefined problem. It's not one of those problems that you go to the back of the book and find out the answer. You're also operating at the cutting edge. Literally, nobody has ever done this before. You are the first people on the planet to look at this problem. Welcome to the real world.
The current global population is at 7.2 billion people and is projected to reach 9 billion by the year 2040. Today, about 700 million people in 43 different countries lack access to clean water. As the population grows, the issue of water scarcity will become increasingly severe, even affecting developed countries like the US. By 2050, only 25 years later, the OECD predicts that half of the world will be stressed for clean water. So what's the solution? Desalination. Desalination is a process of removing salt from salt water. So the technology that we're working on is called mechanical vapor compression. This process capitalizes on the latent heat rejected from the process when vapor is condensed to a liquid. Additionally, we're using forms of waste energy to power the process from sources like refineries or power plants. All of this integration lowers the cost, allows for massive scalability, and provides a much more reliable process.
This is the process flow diagram of the nuclear desalination plant we are proposing. This technology uses energy from the nuclear power plant, and a series of compressors are used in combination with latent heat exchangers to desalinate water. First, the water is treated chemically through standard carbonate and sulfate removal. Then, the water is heated through the sensible heat exchangers and fed into the latent heat exchangers to be distilled. The incoming seawater is heated by exiting distilled water and brine. Additional heat is provided by steam from the nuclear reactor. Once inside the latent heat exchanger, steam is compressed in a blower where the water becomes superheated. The superheated steam enters a desuperheater, producing saturated steam that is returned to the latent heat exchanger to boil incoming seawater. After the steam has been harvested, the more concentrated brine is fed into the next latent heat exchanger. The process is repeated at a slightly higher pressure gradient since the vapor pressure of the water has been decreased. Finally, the distilled water and brine will exit at a high temperature and pressure and will pass through a turbine in order to collect some of the energy. The water is passed through the sensible heat exchanger to heat incoming seawater and exits 2.13 degrees Celsius higher than incoming seawater. The distilled water is then passed on to consumers and the brine is returned to the sea. We determined the optimal percent recovery of the system was 74%. This means that for every gallon of seawater fed into the plant, 74% is made into distilled water. After optimization calculations, we found the cost of water to be 34 cents per cubic meter using nuclear desalination technology. In the future, we will take an integrated approach and use Qatar as our test case. The key features of our project are to use waste heat to desalinate seawater, to use artificial wetlands to purify wastewater, to produce biofuels from municipal solid waste, sewage sludge, and plants harvested from the artificial wetlands, and to use undigested residues from the biofuel process as compost to upgrade poor soil quality.